So hello everyone. So today we shall see the next part of changing the sampling rate of a discrete time signal. So in the last class we discussed about decreasing the sampling rate by an integer factor. Today we shall see the increasing of the sampling rate by an integer factor. Okay. So if you see closely the block diagram for the previous section where we discuss about the decreasing the sampling rate. So it involves some operations which are analogous to the sampling of a continuous time signal. On the contrary, here increasing the sampling rate involves operations which are analogous to D to C conversion, because sampling a continuous time signal is C to D conversion. So here it would be the opposite. We shall see how it is analogous to D to C operation. So first of all, consider a signal x of n whose sampling rate is to be increased by a factor L. Okay, let's use this notation. When we have the upward arrow, we define it increasing the sampling rate. When we have the downward arrow, it denotes decreasing the sampling rate. Okay, so if we consider the underlying continuous time signal, let's say xc of t, so the objective is to obtain samples, define xi of n, I for the increasing the sampling rate, xi of n is equal to some xc at nti, where ti is now t by l, because we want to increase the sample rate of the signal. From the sequence of samples, x of n is equal to xc of nt, right? Because here again we want to use only the discrete time operation, because when you can use in a similar way. So here we can again do in a similar way, that given a discrete time signal, first of all let construct the continuous time signal by using the interpolation, what we had seen earlier, and then resample the signal, the continuous time signal. But we had seen already that it might not be a practical approach. That's why we want to involve all the operation in the discrete time domain. So for this xc of t signal, we want to obtain xi of n, which should satisfy this property from the sequence of samples x of n, which was already sampled at some time capital T, right? Okay, so we call this procedure the upsampling, as vice versa to the downsampling, what we called earlier. So from the above equation, it follows that we have xi of n is equal to x n by l. If we combine this and this equation, so we would have xi of n is equal to x n by l is equal to xc n t by l, where n is equal to 0, plus minus l, and plus minus 2l. Now because this should be an integer, it cannot be a fraction. Otherwise, if it is a fraction, it is of no meaning, right? So let's see. So we can define this equation as, okay, first of all let's see the block diagram, that how we are carrying out this upsampling procedure. So given this x of n, we want to upsample by an integer factor of l, and this gives us let's define this signal xc of n. Okay, so this signal is sampled at with a sampling period capital T, and this signal would have a sampling period Ti as T by L. Okay, so again, if you recall from the last section, we talk about the aliasing phenomena, that where we reduce the bandwidth of the signal before doing the downsampling, so that the aliasing can be removed. In a similar way, whatever be the signal we have obtained here, we will pass it through a low pass filter whose gain would be L and the cutoff frequency would be pi by L. We will talk a bit more onto this parameters of the low pass filter, and this, the output of the low pass filter, is what we would have xi of n. So this block diagram, it is similar to the ideal D to C converter. That's why we are calling it initially that increasing the sampling rate involves operation which are analogous to D to C conversion. And this overall system, we call it the expander. So here xi of n would have the sampling time Ti as T by L. Okay. So this is how we would going to obtain this x of I, and we shall also pay a bit more attention to the parameters we have selected for this low pass filter. And xe, what you are seeing E in the subscript, denotes the expander. That's why we have used this xe. Okay, so let's first of all write that what is xe. So on sampling that and using this relationship, you will see that xe of n is nothing but the signal x at n by L. Okay, excuse me, for n equal 0 plus minus L and plus minus 2L. It would be 0 otherwise. So this would be your xe of n. Right? We can also define this signal by using the impulse function. So equivalently, I can define this signal xe of n as summation over k minus infinity to infinity xk and delta n minus kl. Okay, so this definition of xe of n and this definition of xe of n remains same. Now let's visualize this equation in the frequency domain, likewise what we have been doing most of the time. So in frequency domain, I can write xe of e to the power j omega as summation over n as of the signal xe of n e to the power minus j omega n. Now substituting this xe here, you will get summation over n from minus infinity to infinity, of course, then summation over k xk delta n minus kl e to the power minus j omega n. Okay, now changing the order of the integration, we can write it as summation over k xk summation over n delta n minus kl and e to the power minus j omega n. So this part is, you can equivalently write as e to the power minus j omega n should be equal to kl, then e to the power minus j omega lk. So summation over k xk e to the power minus j omega lk. Okay. And it is nothing but a discrete time Fourier transform of x, where the omega has been changed from omega to omega L e to the power j omega L. Okay, so what you see that x e of e to the power j omega is equivalent to the Fourier this DTFT representation of the sample signal at time dx with the frequency scale version. So frequency transform of the output of expander is a frequency scale version of the Fourier transform of the input, that is omega is replaced by omega L. So that omega is now normalized to omega is equal to big omega Ti. Yeah? So let's see one example that how to visualize this increasing the sampling rate. So let's say we have this continuous time signal, the Fourier transform of the continuous time signal xc of j omega from minus omega n to omega n. Now if this continuous time signal is sampled at some capital time t, so this would be this is how it would look like in the frequency domain omega, right? The periodic samples. Now using this relationship, what we have obtained, the omega would be replaced by omega L onto the x-axis, meaning to say now I can write this omega is equal to big omega Ti. So all these where the signal is going to 0 would be shifted by pi by L, and this is what is happening. So pi becomes pi by L, 2 pi becomes 2 pi L, so it will be drawn like this, xc of e to the power j omega. Now passing this signal through a low pass filter Hi with gain L and cutoff frequency pi by L, you would see it will take only this part, right? And whatever it's there, it would be 0. So this is the idea. That's why we have used this low pass filter, because we want to ensure that the signal should expand. Okay. So this example shows that the block diagram, whatever we had seen earlier, does indeed give an output satisfying xi of n as xc of n Ti. If the input sequence xn, which was sampled at nt, was obtained by sampling without aliasing. So here you do not see the aliasing phenomena. We will also see one of the example that what happens whenever there is some aliasing phenomena occurring in the increasing the sampling rate case. Okay. So this operation in overall we call it the interpolator, and writing the low pass filter, let's analyze this low pass filter which we have defined hi of n as sine pi n by L and pi n by L. Okay, this was the low pass filter we had seen here. Let's call it hi of n. Okay, the impulse response of this low pass filter. So we had seen earlier that this low pass filter can be described by this sine c function. So from the above block diagram, you see that xi of n is basically the convolution of the signal xe of n and hi of n, which I can represent in the discrete time domain as k varying from minus infinity to infinity, xe of k and hi n minus k. Okay. Now Xe of k was equivalent to, if you see this definition, yeah, this one, Xe of k would be x of k by L for k equal to 0 plus minus L and plus minus 2L, and substituting this into this equation we will get summation over k x k by L, and substituting hi with n by changing n to n minus k, we would have sine pi n minus k by L divided by pi n minus k by L for, but this relationship hold only at k is equal to 0 plus minus L plus minus 2L and so on. Okay, let's substitute k by L equivalent to k bar, some k bar. So the summation won't change, it would still be k, it would still be varying from minus infinity to infinity, and inside this we have this x of k bar, and sine, this would change to pi of n minus k bar L by L divided by pi n minus k bar L by L. Now here your k bar would change to 0 plus minus 1 plus minus 2, because k bar is equal to k by L. Okay, so you can use this relationship to interpolate your x of k by passing this low pass filter. Okay. Now seeing the property of this sin c function, from here you would see that for n is equal to 0 it is equal to 1, but for hi is equal to n, for all n is equal to plus minus L plus minus 2L and so on, it would be 0. Okay, so thus for the ideal low pass filter interpolation or low pass interpolation filter, we have xi of n is equal to xn by L, which should be equal to xc n t by L, and finally xc of n ti for n is equal to 0 plus minus L and plus minus 2 and so on. Okay, so this is how you can increase the sampling rate of the discrete time sample by an integer factor L. Okay. Now the last topic of this increasing and decreasing the sampling rate. In the next topic, what we want to see, that initially we had started with decreasing the sampling rate by an integer factor, then increasing the sampling rate by an integer factor. Now what we want to do, we want to change the sampling rate by a non-integer factor. Okay, it could be increasing the sampling rate or decreasing the sampling rate by some non-integer factor which is not an integer. So how to obtain that? So now the idea here is that by using the two previous concepts of increasing and decreasing individually, when we combine those two things, or let's say by combining this decimation and interpolation, it is possible to change the sampling rate by a non-integer factor. So let's see. First of all, given this x of n, we upsample it by some integer factor L, which will give your xe of n, and pass it to the low pass filter with gain equal n and cutoff frequency is equal to pi by L. Okay, this will give you your xi of n. Now we will use the decimator block diagram, what we had seen earlier, that here we pass the discrete time signal by a low pass filter initially in order to decrease the bandwidth of the signal if there is some aliasing, with gain is equal to 1 and cutoff frequency is pi by m, and this we had denoted by putting a tilde over the signal, since here we have xi of n, we will put x tilde I of n. Okay, and then we downsample it by some integer factor m to finally yield the x tilde d of n. Okay, so this block dashed blocks is an interpolator, and this dashed block is the decimator. So let's see what is happening to the sampling time after each and every processing. So here this signal has a sampling period t, xe of n is t by l, xi of n, it won't, this low pass filter won't change the sampling rate, so it would still be at t by l. Again, low pass filter won't change anything, it would be t by l. But here we have the downsample, so it would change to Tm by L, right? So if you have M greater than L, you would see the increment in the sampling period, right? The increase in the sampling period, let's say. And depending on the values of M and L, you can increase the sampling period by some non-integer factor with this operation. And if you have M less than L, of course it would be the opposite, that you would see the reduction in the sampling period. Now if see this block diagram, if I combine, let's use this another pen. If I combine these two low pass filter into one, I can draw the block diagram as given this x of n. So it is passed through the upsample by L, and here it would be some low pass filter whose gain would be equal to L because the gain would be multiplied, and the cutoff frequency is given by the minimum of the dominant frequency pi by L and pi by n, whatever be the minimum, depending on whether m is greater than L or L is greater than m. And finally it is passed to the downsampler of m to yield the signal x tilde d of n. Okay. So yeah, so what would happen if you have m greater than L? So if you have m greater than L, your pi by m is the dominant frequency. It means that for avoiding aliasing, bandwidth need to be limited. And when you have m less than L, in that case you would have pi by L as the dominant frequency. And in that case, you don't need to limit the bandwidth to avoid aliasing, right? We can see one quick example for this combination. Okay, so this figure, so suppose we have a band limited signal with xc j omega is given by this, okay, which is sampled at the Nyquist rate 2 pi by t is equal to twice omega n. Okay, and we know that the dtft of this continuous time signal is given by x of e to the power j omega is equal to 1 by t summation over k of xc j omega by t minus 2 pi k by t. Right? This would be the discrete time Fourier transform of the continuous time signal, and it is given by this one, it is plotted here. So an effective approach to changing the sampling period to 3 by 2, let's say if we want to change the sampling period of the signal by 3 by 2 of capital T, then first we interpolate by a factor L is equal to 2, and then decimate by a factor M is equal to 3, because we have L in the denominator and M in the numerator. So since this implies a net decrease in the sampling rate, and the original signal was sampled at the Nyquist rate, so we must incorporate additional band limiting to avoid aliasing, because here we have M greater than L. Okay, so this figure, the figure C, shows the DTFT of the output of the L is equal to 2 upsampler. We had seen earlier that xc of e to the power j omega would be equal to x of e to the power j omega L, with L is equal to 2. So if we were interested only in interpolating by a factor of 2, we could choose the low pass filter to have a cutoff frequency of omega c equal to pi by 2 and a gain of L is equal to 2. However, since the output of the filter will be decimated by M is equal to 3, we must use a cutoff frequency of omega c pi by 3. But the gain of the filter should still be 2, because likewise we had seen earlier that the combination of the two low pass filter, the gain does not change. So applying this HD to this signal, or multiplying this signal and this frequency domain representation, we get xi tilde, xi tilde of the output of the low pass filter. So you would see, since pi by M is less than pi by L, there would be some cutoff, or not cut. So some part of the signal would be deleted. So the remaining signal would be this one. Okay. So finally, the last figure shows the DTFT of the output of the downsampler by M is equal to 3. When we do this upsampling L by MT. Right? So this gray region, what you are seeing here, that this shows the aliasing which would have occurred if the cutoff frequency of the interpolation low pass filter had been pi by 2 instead of pi by 3. That's why we limited the bandwidth of the signal. Okay, so here we finish the topic of changing the sampling rate by some integer factor and by some non-integer factor. Okay.